Hello everyone, welcome to the second part of the talk, Volume Conjecture, Geometric Decomposition and Deformation of Hyperbolic Structures. First, let me remind you what we have discussed in the previous talk. Last time, we discussed the volume conjectures for the quantum invariants. For hyperbolic logs and lengths, we have the volume conjecture for the colored Jones polynomials at the n+1/2 roots of unity. And the conjecture suggests that for any hyperbolic length L, the nth colored Jones polynomials of L evaluated at e to the power 2 pi I divided by n+1/2 growth exponentially, and the exponential growth rate captures the hyperbolic volume of the length complement. Besides, for hyperbolic three-manifolds, we have the Chen-Yang volume conjecture for the derived free-wheel invariance at the primitive alpha roots of unity as shown in this equation. Furthermore, in 2017, Dacturi, Cavagiani, and Yang proved that the R-derived free-wheel invariance of a length complement evaluated at these roots of unity can be expressed as the sum of the square of the norm of the colored Jones polynomials of the length L evaluated at this n+1/2 roots of unity. In particular, this formula provides a bridge between the volume conjecture of the colored Jones polynomials and the volume conjecture of the derived free-wheel invariance. So far, we have discussed the volume conjecture for the quantum invariance for hyperbolic lengths and three-manifolds. In this talk, we will focus on the following question. What happens if the lengths and three-manifolds are not hyperbolic? How are the asymptotics of the quantum invariance related to the geometric information about the lengths and three-manifolds? To answer this question, we need to introduce the concept of the so-called JSJ decomposition. And to illustrate the idea of the decomposition, let me first discuss an operation or knot called the Whitehead double. Consider the standard genus 1 Higgs splitting of the three-sphere S3, consisting of two solid tori glued together along the torus boundaries. Then we consider the Whitehead length complement in S3. From the Higgs splitting of the three-sphere, we can see that when we remove the tubular neighborhood of this wet component, we will get a wet solid torus with a green clasp inside it removed. Moreover, given any knot, let's say the fragile knot, we can consider its tubular neighborhood in S3, and this picture shows the diagram of the tubular neighborhood of the fragile knot. Now we have a solid torus with a green clasp removed. Besides, we can consider the complement of the tubular neighborhood of a knot. Let's say here we have the complement of the tubular neighborhood of the fragile knot. Since both of them have torus boundaries, we can glue them together in the obvious way to obtain a new knot, and the resulting knot is called the Whitehead double of the knot. This picture shows the diagram of the Whitehead double of the fragile knot, and we will denote this knot by W0111041. Since this picture on the right is obtained by gluing these two spaces together along the wet torus, if we read this equation from right to left, it means the following. We can find a wet torus, which is the so-called essential torus such that when we cut along the red torus, we get these two topological spaces. To be precise, we actually get two hyperbolic D-manifolds. For simplicity, instead of drawing the tubular neighborhood, we'll use the color red to highlight the essential torus. And here, let me give one more remark that the Whitehead double of a knot is also a knot. In particular, we can do the Whitehead double again and again on the knot, and the resulting knot will be called the iterated Whitehead double of the knot. More generally, we can consider the cabling by the Whitehead chain as shown in this picture. Here we have the length W1111 with one full twist, one belt, one cusp, and one mirror cusp. Using the same argument, one can show that this picture also gives us a solid torus. And we can cable this solid torus along the tubular neighborhood of the frigate knot to obtain the resulting length. And we will denote this length by W111141 with one full twist, one cusp, and one mirror cusp. It turns out that this length is not hyperbolic, but we can decompose its complement into these two hyperbolic pieces. In fact, given any oriented, irreducible, and boundary irreducible three-manifold M, just some technical conditions on the three-manifold, there exists a canonical collection of tori such that when we cut along the tori, each piece is either hyperbolic or cipher-fibered. In this talk, we don't need to know what cipher-fibered manifold is. As long as we know what hyperbolic three-manifold is, we can define the volume of the manifold M to be the sum of the volume of the hyperbolic pieces. And this quantity is up to a constant equal to the so-called Gromov law or simplicial volume. And this decomposition is called the JSJ decomposition. With this notion of volume, the volume conjectures for the Color-Jones polynomials and the two-rival invariants naturally extended to any manifolds with finite volume. Moreover, the Color-Jones polynomials is well behaved under the connected sum. The nth Color-Jones polynomials of the connected sum of the lengths L1 and L2 is up to a factor equal to the product of the nth Color-Jones polynomials of L1 and L2. In particular, when T is the n plus 1/2 roots of unity, one can show that this factor grows at most polynomially. So it doesn't affect the exponential growth rate, and the exponential growth rate of these Color-Jones polynomials is equal to the sum of the exponential growth rates of these two. So from now on, we will focus on the quantum invariance of prime lengths, and we are ready to see the main results. First, for the length WA1CD41, the cabling by Whitehead chain along the frigate knot, the volume conjectures for the Color-Jones polynomials of this length, and the volume conjecture for the two-rival invariance of this length complement hold. That means we have the following two equations. And this result actually provides the first infinite family of prime lengths with two hyperbolic pieces in the JSJ decomposition, satisfying the volume conjectures. It is interesting to see if we can find examples of prime lengths with more than 2 hyperbolic pieces in the JSJ decomposition satisfying the volume conjectures. And to construct such kind of examples, we consider the iterated Whitehead double. First, we can consider the iterated Whitehead double of the fricate knot, denoted by WP plus 1, 0, 1, 1, 0, 4, 1, for P greater than 0. And one can show that its complement contains P plus 1 hyperbolic pieces. Besides, we can consider the iterated Whitehead double on the half length, denoted by W alpha beta for alpha beta integers greater or equal to 0. This picture shows several examples of lengths in this infinite family. The first one, denoted by W00, is the half length. If we do the Whitehead double along the blue component of this length, we'll obtain the second picture, and we will denote it by W10. And we know that this length is nothing but the Whitehead length. Next, we do the Whitehead double along the yellow component to obtain the third picture, and we will denote this length by W11. The upper index alpha and the lower index beta are the number of times we do the Whitehead double along the blue component and the yellow component respectively. And the fourth picture shows the diagram of the length W21. With this notation, our result can be stated as follows. The volume conjecture for the Carter-Jones polynomials and the volume conjecture for the trivial invariance of the twice iterated Whitehead double of the fricate knot and for the length W21 hold. And this result provides the first examples of prime lengths with 3 hyperbolic pieces in the JSJ decomposition satisfying the volume conjectures. So far, using the idea of the JSJ decomposition, we have the volume conjecture for the Carter-Jones polynomials for non-hyperbolic lengths. Besides, in the previous talk for hyperbolic knots and lengths, we discussed the generalized volume conjecture, and we expect that the exponential growth rate of the Carter-Jones polynomials capture the hyperbolic volume of the length complement equipped with certain hyperbolic structure. The last thing we want to do is to combine these conjectures together and ask the following question. How about the asymptotics of the Carter-Jones polynomials for non-hyperbolic lengths with limiting ratio not equal to 1? How are the asymptotics of the polynomials related to the geometric information of the length complement? As before, we define S to be the limiting ratio of m to n plus 1/2, where m is a sequence in n. Then we have the following result, which says that there exists delta greater than 0 such that whenever S is sufficiently close to 1, the nth Carter-Jones polynomials of the Whitehead double of the fricate knot and the Carter-Jones polynomial of the twice iterated Whitehead double of the fricate knot grow exponentially, and the exponential growth rates are given by these two equations. These two formulas look very complicated, but they can be interpreted as follows. Let's focus on the Whitehead double of the fricate knot. Recall that the JSJ decomposition of the knot complement is given by this equation. our result basically says that the exponential growth rate of these Calder-Jones polynomials gives us these two terms. And these two terms correspond to these two pictures. The result means that along the red essential torus, the metric is always chosen to be the complete metric. And that's why here, for the second term, we have the hyperbolic volume of the frigate knot complement equipped with the complete hyperbolic structure. Besides, for other components, the choice of the color and the choice of the hyperbolic structure is exactly the same as the generalized volume conjecture for hyperbolic lengths. That's why for the first term, here along the red component, the metric is complete and we have U1 equal to 0. While along the green component, we have U2 equal to 2 pi I times 1 minus S, where S is the limiting ratio. Similarly, for the length W11, we let Si to be the limiting ratios of Mi to n plus 1/2 for I equal to 1 and 2, where Mi's are sequences in n. Then we can show that whenever S1 and S2 are sufficiently close to 1, the M1, M2 Calder-Jones polynomials of W11 grows exponentially, and the exponential growth rate gives us these two terms. And the same interpretation also works for this length. First, the JSJ decomposition of the length complement is given by this equation. Again, along the red component, the metrics are complete, and that's why here we have U2 equal to 0, and here we have U1 equal to 0. And along other components, the correspondence between the color and the choice of the hyperbolic structures is exactly the same as the generalized volume conjecture for hyperbolic lengths. That's why here we have U1 equal to 2 pi I times 1 minus S1, and here we have U2 equal to 2 pi I times 1 minus S2. For the length W21, one can verify that the JSJ decomposition of the length complement is given by this equation. And this time we obtain an extra component, which is a Whitehead length with both components colored by red. And that's why in the theorem below, you can see that the exponential growth rate of the M1, M2 Calder-Jones polynomials of W21 give us an extra term, which is exactly the volume of the Whitehead length complement equipped with complete hyperbolic structure. Finally, let me briefly discuss some ideas about the proof of the volume conjecture for the Calder-Jones polynomials. Here is the strategy of proving the volume conjecture. First, let's say given the M1, M2 Calder-Jones polynomials of the Whitehead length evaluated at this n plus 1/2 words of unity, using some technical arguments involving the use of the quantum dialog function and the Poisson summation formula, we can write the Calder-Jones polynomials in an integral form f times exponential of n plus 1/2 times another function phi s1 s2 of the Whitehead length WL, and it is a two variables holomorphic function in Z1 and Z2. Once we write the Carter-Jones polynomials in an integral form, we can apply the so-called settled point approximation, which essentially says that the asymptotics of this kind of integral is determined by the critical values of this function evaluated at certain critical points. And since this function is so special, we give it a name and call it the potential function of the Whitehead length. And this point z s1, s2 is certain critical point of the potential function. To find the critical point of the potential function, we consider the critical point equations ddz1 of phi equal to ddz2 of phi equal to 0. The exponential growth rate is then determined by the real part of the critical values of the potential function. Besides, there is also a system of equations coming from the geometry of the length complement. From the work of Thurston, we know that the Whitehead length complement can be obtained by grouping the faces of an ideal octahedron. Here, we group the faces A1 to A2, B1 to B2, C1 to C2, and D1 to D2. To give it a hyperbolic structure, we decompose the ideal octahedron into 5 ideal tetrahedra and assign shape parameters to them according to the following rules. Here, the shape parameters depend on the variables z1 and z2, and also the limiting ratios s1 and s2. In order to obtain a geometric structure for the length complement, the shape parameters have to satisfy the edges equations HE equal to 2 pi I for all edges, where HE is the holonomy around the edge. It turns out that with this particular choice of triangulation of the length complement, together with this particular assignment of shape parameters, there is a correspondence between the critical point equations and the hyperbolic Boolean equations. Here, by hyperbolic Boolean equations, we mean the set of all edges equations together with 2 additional equations describing the holonomy of the meridian along the belt and the holonomy of the longitude along the clasp. Finally, the potential function satisfies the following differential equation. If we write zk equal to xk plus iyk for k equal to 1 and 2, then the real part of the potential function can be written as 1 over 2 pi times the sum of the volume of the tetrahedron with the prescribed shape parameters plus the sum of yk ddyk, real part of the potential function. In particular, at the critical point z s1, s2, since it is a critical point, we know that the second part vanishes. Furthermore, due to the correspondence between the critical point equations and hyperbolic Boolean equations, we know that the first term gives us the sum of the volume of the tetrahedron with the shape parameter satisfying the hyperbolic Boolean equations. And that's why the real part of the critical value of the potential function gives us the hyperbolic volume of the Whitehead length complement equipped with this particular hyperbolic structure. And that's all I want to discuss today. Let me thank the organizers again and thank you all for your attention.